And now that we know how to publish a static transform between any two frames using the static transform broadcaster class, let's add some functionalities to our Python node that will make it also publish a dynamic transform between any two frames. If you're only interested in the C++ development, then you can skip to the next lesson in which we are going to implement the same functionalities in C++. So let's keep adding functionalities to the BumperBot.py examples package and to the Simple TF kinematics class. Here, not only we want to publish a static transform within the TF static topic using this object here, but also we want to start publishing a dynamic transform which changes over time. Whether to publish a static transform, we used the static transform broadcaster class that is in the TF2 ROS library. To publish a dynamic transform, let's use instead a transform broadcaster object. So still from the TF2 ROS library, let's import the transform broadcaster object, so this here, and let's create a new instance of this class as a member of the Simple TF kinematics class. So let's go here and let's call this new variable dynamic TF broadcaster, and this is an instance of the transform broadcaster class, and also this one receives as input the current object, so the self variable. Then we need to create another message that this time will contain the transform that we want to publish in the TF topic. Also in this case, this message is an instance of the transform stamped message, so of this interface here. So we can create a new message and let's call this one dynamic transform stamped. So also this one is an instance of the transform stamped interface. And since we want to repeatedly publish the dynamic transform to simulate the relative movement between two frames, we can use our ROS2 timer to execute repeatedly a certain function. So here, after the getLogger function, let's create a new ROS2 timer. Let's call this one timer, and we can initialize it with the function create timer, which we are still inheriting from the node class. And let's set the duration of this timer to 0.1 seconds. So every 0.1 seconds we're going to publish a new transformation between two frames. And also when this timer expires, we want to execute the function timer callback, so this function here. And so let's actually define this function still as a member of the Simple TF kinematics class. So like this, and within this function, whenever the timer expires, we want to publish the new transform, and so the new transform stamped message in the TF topic. So before defining the behavior of the timer callback function, let's fill the dynamic transform stamped message with some information about the transform that we already know at the moment of the construction of this message. So we can add it here, for example, and let's initialize of the dynamic transform stamped message. Let's initialize, for example, the header stamp message, and we can take the current ROS2 time by copying the same instruction that we used for the static transform stamped. And also let's set the frame ID, so of the dynamic transform stamped in the header. Let's set the frame ID, which is the parent, and let's call this odom. So let's call this frame odom, and then let's also set the child frame ID. So still for the dynamic transform stamped, let's set the child frame ID, and for example, let's set this one to be the BumperBot base frame. So while this transform here, so the static transform, is connecting the parent, which is the BumperBot base, to the child, which is the BumperBot top, this dynamic transform will connect the parent, which is a new frame called odom, still with the BumperBot base frame. And so this one will be our dynamic connection. So this one will be our dynamic frame that will move. Within this function, so within the timer callback function, we can start initializing the dynamic transform. So let's set for the dynamic transform stamp, the first thing that we can set is the timestamp, and in order to set this equal to the current ROS2 time, we can exactly copy this instruction here that we have used for the static transform, and so this will provide the current ROS2 time. Then let's also set the base frame ID, so the parent. So still from the header, let's access to the frame ID, and let's set this one equal to the new frame called Odom. And then let's also set for the dynamic transform stamped the child frame ID, and let's set this one to the bumperbot base frame. So now the static transform will publish the transform between the bumperbot base and the bumperbot top frame. Instead, the dynamic transform will publish a dynamic transform between a new frame that we have called Odom and the bumperbot base frame that we have already declared here. So this will be the parent of our tree, then this will be its child, and this one will be a child of the bumperbot base. So the bumperbot base will be itself a child of the Odom frame, and also the bumperbot base will be simultaneously also the parent of the bumperbot top. Now let's also set the properties of this transformation, and so the transformation matrix. So the dynamic transform stamp, let's access to the transformation, and let's set first the translation vector. So it has three components, which are the X components, then the Y, and finally also the Z. And here we want to simulate the movement of the bumperbot base frame with respect to its parent, so to the Odom frame. To do so, we need to add two more support variables that we can still define and initialize within the constructor of the Simple TF kinematics class. So let's do it here. The first one indicates the increment that we want to add to the transform at any iteration of the timer. So let's call this variable X increment with the letter C, and let's set this one to 0.05. So every time we execute the timer callback function, the child frame ID, so this one, will move 0.05 centimeters. And then let's also create another support variable, and let's call it last X, and this will contain the last known value of the transform along the X direction that will be used to calculate then the next position, so the next value of the translation along the X axis. Since we have not published any transform yet, let's set this one equal to 0. Now we can use these two variables to assign a value to the translational component of the transformation along the X direction, so this one here, and let's set this one equal to the last position, so the last X, plus the position increment, so the one that we have called X increment, and so this will be the new value of the translation along the X-axis. So every time we will call the timer callback function, we will calculate a new value for the translation along the X-axis. Instead, let's keep the translation along the Y-axis and the translation along the Z-axis equal to 0. As for the rotational component of the transform, let's also set the two frames Odom and bumperbot base frame to be oriented the same way. So still we can access to the dynamic transform stamp and to the transformation matrix, and let's access to the rotation matrix. And actually this is a quaternion that is composed of 4 components, and these are the X, the Y, the Z, and the W component. And the first one is set equal to 0, the second one also is set equal to 0, and also the third one. And instead, to indicate a 0 rotation, let's set the last one equal to 1. So this means that still the bumperbot base and the Odom frame will be oriented the same way. Now we have completed the dynamic transform stamped message, so this one that we can publish in the TF topic. To do so, we can use the dynamic TF broadcaster object, and on this one we can execute the send transform function to publish the dynamic transform stamped message that we have been creating so far. Before the end of the timer callback function, so here, let's keep in mind that we need to update the value of the last x variable, so this one, to the current value of the transform. So let's access to the dynamic transform stamped, and then to the transform, and then to the translation, and to the x component. With this we have done, and so we have added a timer to the simple TF kinematics class, which publishes regularly, every 0.1 seconds, a new transform in the TF topic between the odom and the bumperbot base frame, which constantly increments the translational components, so this one along the x-axis of the bumperbot base frame with respect to the odom frame. Now let's see how all of this works by opening a new terminal, and let's go into the workspace and let's build it. Then we can open a new window of the terminal, and actually before starting our node, let's start and configure rvis2. So here in rvis2, let's start by changing the fixed frame to be the odom frame, which is the first frame that we have defined in our tree. And also let's add the TF plugin like this. Now let's set rvis on one side. Okay. And now we can finally start our node. So in a new terminal, let's source the workspace and let's run. So ros2 run from the bumper.py example. Let's start the simple TF kinematics node. So let's press enter, and now we can see that we have 3 frames. So we have like this. Let's display the names. Okay. So we have here the odom frame, which is fixed, and here we have 2 frames that are moving, the bumperbot base and the bumperbot top. And so we can see how the bumperbot base frame is constantly translating with respect to the odom frame in the x direction, so along the x-axis. Instead, we can see that still the transformation between the bumperbot base frame and the bumperbot top frame is static. So we can see that the bumperbot top frame doesn't move, doesn't translate with respect to the bumperbot base frame. So they move together. It's like if they are screwed together. In this moment in rvis, we are visualizing both the static transform between the bumperbot base and the bumperbot top frame, and the dynamic transform between the odom frame and the bumperbot base frame, which is the one that is changing over time. And so simultaneously we are seeing all the messages that are published within the TF and within the TF static topic.